Hello students, my name is Abdullah Momin from KMES English Medium High School and Junior College, and in this video we are going to see the numericals part 3 of the chapter Superposition of Waves. So in our last lecture we have completed the numericals till 6.8. Now we are going to start the next numerical from your textbook, that is example 6.9, and it is on your textbook page number 149. So what is the question? So example 6.9, a sonometer wire of length 50 centimeter is stretched by keeping weights equivalent of 3.5 kg. The fundamental frequency of vibration is 125 Hz. Determine the linear density of the wire. So what is given here? Here the length of the wire is given, which is L, and it is stretched by keeping the weight of 3.5 kg equivalent. So if the weight is given in kg, that means it is mass, and in order to convert this into weight, we are going to multiply it by g, that is acceleration due to gravity. So here L is given, which is equal to 50 centimeter, and 50 centimeter, when it is converted into meter, it can be written as 0.5 meter, and the weight is equivalent to 3.5 kg. That means the formula of weight, or we can say that tension, can be written as mg. So here mass is given 3.5 and g can be taken as 10. So when 3.5 is multiplied by 10, it will become 35. So tension in the string is 35 Newton. So the next thing which is given, that is the fundamental frequency of vibration, and it is denoted by n. We are supposed to find out the linear density, means small m, and we know the formula of fundamental frequency of the wire, that is n is equal to 1 upon 2L root T by m. So that is the formula which we are going to apply here. So we will say that the given quantity's length is 50 centimeter, which is 0.5 meter. Tension is 3.5 kg into 9.8. So here the acceleration due to gravity is 9.8, and when you will multiply it, you will get 34.3 Newton, and the fundamental frequency is 125 Hertz. So this is the formula of fundamental frequency of the wire, and in this formula we are supposed to find out n, and m is in square root. In order to remove the square root, we are going to square this equation. So n is square 1 upon 4L square T by m, and now m goes to another side of the equal sign, and n square comes down to another side. So in place of m, we can write n square, and in place of n, we can write m. So now the formula of m can be written as T by 4n square L square. T is 34.3. 4n square means 125 square. L square means 0.5 square. And when you will calculate this, you will get linear density as 2.195 into 10 raised to minus 3 kg per meter. So this is the value of linear density of the wire. Now the next numerical which is given, that is numerical 6.10, exercise 6.10, and it is on the textbook page number 150. So what is the question? Two wires of the same material and the same cross section are stretched on a sonometer in succession. Length of one wire is 60 centimeter and that of the other is 30 centimeter. An unknown load is applied to the first wire and the second wire is loaded with 1.5 kg. If both the wire vibrates with the same fundamental frequencies, calculate the unknown load. So what is given here? Two wires are given to be of the same material and having the same cross-sectional area. That means their linear density is same. Now their fundamental frequency is also same. So N1 is equal to N2, which can be written as N. Now the length of the first wire is 60 centimeter, which is converted into meter, that is 0.6 meter. And the length of the wire 2 is 30 centimeter, which can be written as 0.3 meter. And the tension is given in kg. So in order to convert this into Newton, we will multiply it by 9.8 and that will become in Newton. Now for the first wire, we can write N1 is equal to 1 upon 2 L1 root T1 by M1. And for the second wire, we will write N2 is equal to 1 upon 2 L2 square root of T2 M2. And by dividing these two equations, this 2 and this 2 will get cancelled. And the denominator of the denominator means L2 comes into numerator. And this M2 also goes to numerator. That means now the equation can be written as N1 by N2 is equal to L2 by L1 square root of T1 into M2 divided by T2 into M1. Now, after dividing the first and second equation, we are getting this equation, that is N1 by N2, which is equal to L2 by L1 square root of T1 into M2 divided by T2 into M1. Now we are going to put the values. The fundamental frequency of both the wire is same, so we will write N upon N. Their length is 0.3 and 0.6. So we will going to put the values of length of the wire. T1, which we are going to find out. M, their linear density is also same. So instead of M2, we will write M. Instead of M1, we will write M. And T2 can be written as. So this N and this N, this M and this M get cancelled. We will write 1 is equal to this 0.3 ones are 0.3, 0.3 twos are 0.6. So that becomes 1 by 2 root T1 upon this 2, which is in denominator, goes to another side of the equal sign and it becomes 2. And in order to remove this square root, we are going to square this equation. So 2 becomes 4 and this square root get cancelled after applying the square on both sides of the equation. Now T1 can be written as this denominator goes to another sign and 1.5 into 4 is 6 into 9.8 Newton. That means it is 6 kg. 9.8 we will going to remove this part and the remaining part is your mass, means the tension which is equivalent to 6 into 9.8 Newton is 6 kg. Now the next example is 6.11, which is on textbook page number 150. And the question is, a wire has linear density 4.0 into 10 raised to minus 3 kg per meter. It is stretched between two rigid support with a tension of 360 Newton. The wire resonates at a frequency of 420 Hz and 490 Hz in two successive modes. Find the length of the wire. So given that the linear density is 4.0 into 10 raised to minus 3 kg per meter, the tension is 360 Newton. Let the wire vibrate at 420 Hz and 490 Hz in its pth and pth plus 1 harmonic. Then NP is equal to NP, where N is the fundamental frequency. So we will write the formula of fundamental frequency n is equal to p upon 2l root t by m. This is the formula of fundamental frequency of pth harmonic. This is for pth harmonic, and this formula is for p plus 1 harmonic. Now dividing these two equations, when you will divide this equation with 420 is equal to p upon 2l root t by m. So root t by m and root t by m get cancelled. 2l and 2l get cancelled, and we will get 490 hertz divided by 420 hertz is equal to p plus 1 upon p. And after solving this, we will get n as 6. Now using this value of p for the frequency of pth harmonic, we can write this is the frequency of pth harmonic. We will write is as np. This is the value of np. That means pth harmonic. So instead of p, we are going to put the value 6. So when you will put the value 6 and we will calculate it, we will get 900 meter per second. And after dividing it, calculating it, we will get the length 2.14 meter. So this is your example number 6.1. Now example 6.12, which is on textbook page number 153. And in this example, there are two sound waves having wavelength 81 centimeter and 82.5 centimeter. And when they will superimpose this, they will produce 8 beats per second. Calculate the speed of the sound in air. So we will write that the wavelength that is for first wave is lambda 181 centimeter, which can be written is in meter as 0.81 meter. Lambda 2 82.5 centimeter, which can be written as 0.825 meter. And we know that V is equal to N1 lambda 1, that is for first wave. So N1 will be as it is. Take lambda 1 to another side of the equation. So we can write the equation of N1 as V upon lambda 1. So we are going to use this equation over here. So N1 is equal to V upon lambda 1. So V upon 0.81. Similarly, N2 can be written as V upon lambda 2. That is V upon 0.82. Since lambda 1 is smaller than lambda 2, that means N1 should be greater than N2. Because n and lambda are inversely proportional. If lambda 1 is large, that means frequency is small. If frequency is large, that means wavelength is small. So both quantities are inversely proportional. If second wave is having larger wavelength, that means its frequency is smaller than first one. So now when they will superimpose, they are producing a beat of 8 per second. That means N1 minus N2 is 8. Now instead of N1, we are going to put V upon lambda 1. And instead of N2, we are going to put V upon lambda 2. So it can be written as 8V, and V is, we are taking V common, 1 upon lambda 1 minus 1 upon lambda 2. Now instead of lambda 1, we are going to put the value 0.81 meter, and instead of lambda 2, we are going to put 0.825 meter. And after cross multiplying it and calculating it for V, we will get V as 356.4 meter per second. This is the speed of sound in air. So the speed is 356.4 meter per second. Now this is the last exercise question from your textbook, that is exercise 6.13, and it is on the page number 153 of your textbook, and the question is: two tuning forks having the frequency 320 Hz and 340 Hz are sounded together to produce a sound waves. The velocity of sound in air is 326.4 meter per second. Find the difference in the wavelength of these two waves. So what is given here? We will say that the frequency of first wave is given, that is 320 Hertz. The frequency of second wave is also given, that is 340 Hertz. And the velocity of sound is given, which is 326.4 meter per second. And we know that V is equal to N1 lambda 1 and V is equal to N2 lambda 2. V will be constant. If you will increase the frequency, wavelength decreases. If you will decrease the frequency, wavelength increases. So since from the given data, we will say that N2 is larger than N1, means lambda 2 should be smaller since the frequency is greater. Increasing the frequency decreases the wavelength. So if you will increase the frequency, wavelength decreases. If you decrease the frequency, wavelength increases. So we will write lambda 1 minus lambda 2 as V by N1 minus V by N2. From this equation, we can write lambda 1 is equal to V by N1. So V by N1 minus V by N2. So instead of V, we are going to take V as common, and instead of N1 and N2, we are going to put the values, that is 320 and 340. And after calculating it, we will get the value of lambda 1 minus lambda 2 is equal to 0.06 meter, and this is the difference in the wavelength of the frequencies. So the difference between the wavelength of these wave is 0.06 meter. So that's it, student. Thank you very much for watching this video. Now this is the last part, since we have completed the numericals also.